Hello, everyone. My name's Bill. I am an engineer at Twitter, and I've been working on Apache Aurora for almost 4.5 years now. Aurora is kind of similar to a couple of other things we've talked about today. It's a service management framework. We were kind of very early on in adopting Mesos. Basically, we hired Ben fresh out of Berkeley. I guess he was still a student at Berkeley when we sort of brought him in. And specifically today, what I want to talk about is kind of what we've been up to for those 4.5 years of development. I've said before in talks I've given about Aurora where we haven't actually been spending all of our time building out a huge feature set. We've actually really been focusing on robustness because we really had a goal of running all of Twitter on top of Aurora and on top of Mesos, and basically making those a cornerstone of Twitter infrastructure. And I'm happy to say we're really, really far along on that path, and I'll talk a little bit more about that later. There's sort of a lot of software engineering. There's a lot of corner cases you have to cover in order to build something that you're comfortable running a site like twitter.com on top of. So that's why it's taken us so long, and we've had to work so hard to get there. And what I want to talk about is different aspects of scale. A lot of time when talking about distributed systems, scale is basically workload or machines. And that's definitely one aspect of it. On the Aurora team, we like to think about a couple of other aspects of scale as well. We want to really focus on organizational scalability. So we want to make something that's really, really multi-user friendly, that we can take a brand new intern fresh out of college, give them basically unfettered control on this system, and basically make sure that they're not going to cause something catastrophic to the site. Specifically within the Aurora project, we also worry about scalability of our code base. If we end up in a development gridlock, that's a big problem for Twitter. So we've tried to architect our code in a way that we can add new features and without really having to do any major refactors throughout the system. And this is actually really good in open source as well, because it's fairly easy for people to add new features if they want to and customize the scheduler. So yeah, we really want to make the code base scale as well. And as it turns out, that helps a lot for open source and adding new features. So what I'm going to do is sort of give a peek under the hood of the Aurora scheduler. There's a lot more to Aurora that I'm going to talk about today, but specifically I'm going to focus on the scheduler and the internals of that, and basically how it works, how we make it reach that kind of stability that we can trust twitter.com with it. So this is a very flattering architecture diagram. There's a lot more interconnects than I'm showing here, but this is kind of the gist of it. The missing player here is dependency injection. I know a lot of people dislike DI and specifically dislike juice. However, we found it to be really, really powerful and lets us add and remove components without having to have sweeping changes throughout our code. So the major theme here is there's a big bar down the middle that's the event bus. This has become an emergent pattern I've noticed in a lot of projects, and I know I think Marathon uses event bus, but it's been really nice to allow us to decouple the different components of our system. So fundamentally what we have is there's our inputs to the system, which there's an HTTP interface and libmesos. This is probably pretty common amongst different frameworks. There's a series of state machines, which I'm going to discuss in more detail later, and what exactly that means, what those state machines do. And then there's a lot of events being published to this bus that other things can subscribe to and basically deal with state changes as they see fit. And then there's a whole slew of things on the right side that I'm going to talk about specifically in detail. And then the mammoth of the system is really the storage, and there's a really long history there and a lot of diversity there in the past. So I'm going to be discussing that in a lot more detail. So one of the robustness features that we've built in is a task timeout, and this is nothing unique to Aurora. In fact, I'm sure a lot of these concepts that you see here are very common to any distributed scheduling system. These are just problems that you have to worry about. So basically what the task timeout does is notices when tasks enter a transient state. So we have basically an enum of states that tasks in Aurora can be in, and that's basically a superset of the tasks that you see defined in Mesos. So one of the states that we put a task in is assigned. So this is we've allocated a resource, we've accepted an offer, and now we're waiting to hear back that that task is actually executing. And basically what we do there is we set a trigger, and at some point in the future, if we notice that task has not yet changed state, we consider it lost. And this basically allows us to adapt if, for example, we accept that offer and the Mesos master was down at that time, or basically anything in that entire chain that's required for launching a task goes wrong, we can adapt to that and we can deal with it. One of the big features in Aurora that is actually really important for running it in a way that we have both production critical applications and just toys that any old developer is running is preemption. And basically the job of the preemptor is to make room for production applications. So what this is going to do is look around, try to find an open resource slot for a task first when it's production. And if it can't find one, it's going to go hunt for other tasks that it can kick out to make availability for those resources. And this is also important so that we can do things like tell interns, well, actually not tell interns that they have limits, just let them do whatever they want, or let any developer take whatever resources they want. But we're going to be provisioning for the production applications. So basically what production is doing, there's a quota system that I'm kind of glossing over here, but applications are, or actually users are allocated resource quotas, and by scheduling a production job, you're consuming that resource quota. And that's basically how we make sure that we can always have enough resource to run all the things that are really important. So we have also a component that deals with providing advice about scheduling. This is really part of the organizational scalability. When somebody schedules a task or schedules a job and it's pending forever, we don't really want them to email us or page us, God forbid, about why it's pending. So what we do here is we actually look at, when we're trying to fit a task against an offer, what actually caused it to not fit. And then we can surface useful information like a rack limit not being satisfied, or you've requested too much CPU, we don't have as much CPU as you wanted. And this has actually allowed users to basically figure out how to fit their applications on their own. Another feature I'm sort of glossing over here is the constraints. So similar to Marathon, we have constraints where you can do things like rack diversity and host diversity. So when somebody has basically more tasks than we have machines in the cluster, they might see this limit not satisfied issue where they wanted pure rack diversity, but as it turns out, we don't have that many racks. So this is really useful so that people don't have to really know the shape of the cluster or know the shape of the machines, but they can adapt when they don't fit. There's a whole slew of stats that Aurora exports. One of the most recent interesting additions is SLA-based stats. These are really cool because these are per job stats where we basically show you how your job looks with respect to uptime and with respect to downtime. And this is cool because there's sort of two angles to this. There's uptime, which is this is sort of a combination between impact by user actions, such as doing deployments, or actual service instability, or even maintenance in the system. So basically, we allow users to get visibility into the uptime in terms of percentiles, so they can see, like, if you sort the uptimes of all my tasks, what is the 99th percentile uptime? And as I'll describe later, that's actually kind of an important feature when you get pretty far down the road. And then the downtime aspect of it is also interesting because this is basically how we, the Aurora team and the Mesos team, hold ourselves accountable for things like maintenance to make sure that we're not being too disruptive of things that are running in the cluster. And one of the things that we really want to do is use this in the future for a lot more automation. We do have like support for rolling upgrades in Aurora, but as it turns out, people either are not terribly good at specifying the parameters for updates, or they just don't want to. So what we'd like to do is start focusing on basically utilizing these SLA statistics and utilizing some SLA requirements from our users, and use that to do different things like control rescheduling rates, and control rolling upgrades. So it's a long ways down this list, but scheduling is obviously one of the core components of the scheduler. So that kind of deserves its own little diagram. So there's sort of a lot going on inside of the scheduler, and I've drawn the event bus here again. And basically, what we do to make the scheduler robust and do things like allow users to schedule tens of thousands of tasks without impacting each other, basically fencing across users and across jobs, is we organize tasks into groups. So these groups are basically, it's literally just object equivalents among the task descriptions, and by that equivalence, we know those tasks are going to schedule in exactly the same way. And this is really useful because, like I said, somebody can create a job with 100,000 tasks, and it's actually not going to starve the single super important mission critical task that failed and needs to be restarted. We're actually going to timeshare across those. And this is a really, really big feature. This basically allows us to not let users disrupt each other in ways that they might not expect. So down in the sort of bottom right here, there's a very small and insignificant looking component, but this is actually really huge. The previous talk spoke about basically the complexity of scheduling and the trade-offs that you have to make and how it can be very CPU intensive. And that's basically what's going on here. The very simple, naive approach is to just say, does this thing fit? But there's more to that. We have all these scheduling constraints we have to satisfy. And we also do basically machine maintenance. So Ben, at the very beginning of the day, spoke about maintenance controls. This is something that we currently support in Aurora, and actually are kind of excited about deleting that code. But there's a lot going on in that small component that are really important and actually is very complex and CPU intensive. So that's why we have to timeshare at that level up above. We have a module that's responsible for pruning tasks. So all of Aurora's storage, it has to be populated into memory when it starts up. So obviously, we have to figure out a way to cull that memory so that we don't run out of memory. So this is basically a trade-off between providing users detail about what has happened in the past, giving them sufficient history to know how their application has behaved over time, but also not store infinite history and not exhaust our memory. Another thing discussed in the last talk was about the basically reconciliation issues with Mesos. The reconciliation API is basically brand new. Hasn't existed for the last 4 years. So we compromised by building what we call the GC executor. And this is basically our means to shoot the other node in the head. So when we notice these state inconsistencies where we have duplicate instances or orphaned instances, this is how we correct that. So it's kind of a trade-off in terms of time. We do it very gradually, but we do want to converge back towards what the user actually requested. And then throttling is a very important thing as well. This sort of relates back to the complexity of scheduling and how CPU intensive that is. So when we've noticed an application is restarting frequently, and this doesn't matter if the task failed or if it succeeded based on the exit code, we don't really care. We don't want to allow one task or one job to dominate the entire CPU of the scheduler. So as things restart, we notice sort of how long they actually successfully ran, and we'll start to exponentially back off on them to give them less and less CPU time because it's highly unlikely that they're going to recover if they keep failing over and over. So the state machines. This is an interesting part of the scheduler. This has been around probably for about 4 years, and I think this is one of the parts of the scheduler that I'm most proud of because it really hasn't changed much in those 4 years. And I think this is something that's really powerful. It's what made Aurora very, very predictable. It's very easy to know based on events how the scheduler is going to perform. There's not multiple different code paths that define how you go from one state to the other. And basically what the goal is of this is to take the current state of a task, take the proposed state, where a proposed state could come from a user, such as an RPC. It could come from Mesos, or it could come from our storage. And what it does is it figures out what side effects it needs to take to make that proposal actually become reality. And sometimes that means denying the state transition. If the transition is just invalid, we don't actually want to take it, but we might still have side effects we want to perform. A case of that would be if something is in a terminated state as far as the scheduler is concerned, and something else is saying this task is actually running, well, we don't want to bring it back. We don't want to resurrect a task. We want to kill it because we've probably taken some other action to correct, to resurrect that task already. So an example of that, or another example, is if the current state of a task is running and we get a notification from Mesos that that task is lost, we're going to record that state in our storage and we're going to reschedule it. So it's very, very simple. We basically have this full matrix filled out, so we know exactly what's going to happen when we get a new input based on our current state. The primary user-facing input to Aurora Scheduler is HTTP, so we have a web interface. We also have a Thrift JSON interface, which we're slowly trying to make that more user-friendly. One of the artifacts of coming out of Twitter's sort of internal repository and internal infrastructure is we sort of have a lot of that Twitter history along with us. And within an organization, I think things like Thrift actually make a ton of sense. They make a lot of things much, much easier, Thrift and Protobuf alike. But once you're an open source project and you have many, many more diverse use cases to adapt to, I think HTTP and JSON start to make a heck of a lot more sense. So we're sort of gradually moving back towards that so that people can interact with the scheduler more easily. So, and there's been recent development here. I added a sort of a human-friendly aspect. For those of you that aren't familiar with Thrift's JSON protocol, it's basically completely human-unfriendly JSON, but that's not Thrift's fault. Thrift operates on the concept of message IDs rather than human-readable strings, and that's actually really, really important to its protocol, and that's sort of its domain. But I've adapted that to basically make that human-friendly and expose things in keys that people can interact with. And if you're interacting with this API, you actually never know that you're using Thrift. It's all just traditional JSON. libmesos is the other big input to the system. You're probably all familiar with that if you've written a framework before. And if you've been reading the Mesos users list, you've probably noticed that there's been sort of a push to do more language native implementations of this. We've started work on that as well, and we're hoping to replace libmesos with a Mesos framework API that we've worked on. And yeah, if you've read the users mailing list or if you've used libmesos, you'll see how it's a really, really great start. And it really, I mean, obviously it's taken us along for 4 years, but there's a lot of reasons why it's actually easier in many ways to deal with this thing when you are not dealing with a native library. And now the storage. So a lot of other frameworks that I've seen use, they tend to use Zookeeper for storage. We considered that very early on and also discarded it. But basically, so going all the way back to the beginning of time as far as Aurora is concerned, Aurora was first developed, the first commit was in April of 2010. And the first storage was very embarrassing. It's basically just maps and Thrift objects written to disk. But it was a proof of concept, and that was all it was really for. And as you can see, that didn't get us very far. Basically, we were just in prototyping phase. And pretty early, we realized we really need to sort of put a database on top of this. So we have, at that point, in, I think, February of 2011, we adapted that to use H2, which is a pure Java database, and basically using it as a key value store. So, and the real big aspect to Aurora storage is all tasks. So we basically just use the key value store, task ID to byte array. And this got us pretty far, and it like got us away from having to do like schema migrations and schema management within the database. And unfortunately, that ran into CPU bottlenecks pretty fast. Doing that serialization and deserialization so frequently, whenever you're round tripping through your storage, was really, really costly. Oh, and I guess I'm getting ahead of myself. At that point, we realized, okay, we've got this decent data store, but we're not highly available. So before we could do anything serious with Aurora and Mesos, we really needed a highly available scheduler. So at that point, a former developer on our team, John Sorois, worked with Ben Heineman to build the replicated log. So if you've ever seen that interface before, seen that support in Mesos, that's basically the beginnings of the replicated log. And we quickly picked that up. Like we were the first adopter. I guess we were one of the first frameworks, or only frameworks at that time. So we started using that to persist our objects. We have this replicated log that we can then recover, load up our state in memory when we fail over. And so then this is the point I was talking about with regards to CPU. So we had all these CPU troubles with persisting and querying out of the database, so we replaced that with basically hash maps on top of the log. And this was just a huge performance boost, probably 2 orders of magnitude. So this was great and got us pretty far. And then we needed to add backups and recovery because the replicated log doesn't provide that, and we really want to be able to deal with basically bugs and recovering our state when we have to. And now, as you can see, we're back to H2. And there's some good reasons for that. We're working on this right now. I sent a pretty long email to our Apache Aurora users list. And basically, the problem was, at the beginning of this, I talked about making our development scale and making our code scale. And ultimately, what I found was that we were spending so much time implementing a database. So I wanted to stop doing that. I wanted to focus on building a really awesome scheduler and not worrying about indexes and schemas and transactions. I was really interested in just offloading that and letting some other really good project deal with that. So we're back to H2. However, we're using it in a very different way. As I mentioned, we were originally using it just as a key value store and basically just to provide those transactions. And now we're picking it up again and using it in a more relational way. And I think this is really good because it's going to allow us to store a lot more information. We can store a lot more history. We can support many, many more tasks in our memory without having to worry about doing fancy tricks to try to sort of collapse objects together and basically re-implement relations. And going forward, we're not really sure where we want to take this, but there's still one remaining issue that I'd like to fix, is that we still have to figure out a way to persist our state to that log. So we really haven't gotten out of the woods yet with regards to saving ourselves all the development effort when it comes to schemas. So we don't really know exactly where we're going to go here. We're going to explore. There's ways that you can put H2 in high availability mode. We might try to layer that on top of the log in some creative way. But really, we want to avoid making installation burden for users by making them install Postgres or MySQL if we have to. But you know, there's a chance it might come down to that, but that's really going to be something in the future that we'll have to figure out. So I mentioned in the beginning that Aurora and Mesos have become a cornerstone of Twitter's infrastructure. And sometimes as a listener of a talk, it's kind of hard to tell what that exactly means. Like, what are you doing with this software for real? So I came up with sort of an investment scale where on the far left-hand side is nothing, not interested, not using the technology at all. And on the right hand is literally everything runs on top of this system. And there's a couple of gradients that I've defined within there, purely arbitrary. But this is kind of how the evolution has looked as we've adopted this software at Twitter. So in the early days, we started with just sort of non-essential batch things that, you know, if they're down over the weekend, it's not really going to matter. There's no pager attached to this thing. And then you move on to internal services. So things that are kind of interesting, but again, if they go down, it's not a big deal. So we can take these things down for maintenance, or if we have some crazy bugs in the scheduler or in Mesos, it's not really catastrophic. And this is great because this allows you to iterate on the software without having really high stakes and having like CEOs breathe down your neck. And after that, you start to get to sort of best effort services. So these are things that can go down, the site might gracefully degrade, but again, not ultra critical. So you're probably in like hours of downtime as opposed to days of downtime acceptance. And then maybe at that point, all of your batch stuff is on there, so even the important batch. And then this is kind of the real inflection point is critical stateless services. So this is the point where the site will go down when your software fails. And that's a pretty scary step to take. And then beyond that, you get to the sensitive services. So in Toby's talk, he mentioned snowflakes. I totally agree, and in the Aurora team, we've been really, really insistent on this to try to de-snowflake things as much as we possibly could. But they're always there. You're never, ever going to get rid of them. There's always going to be something that either needs to be up all the time or needs to be up some certain amount of time before you take it down. A great example there is things like caches, where if you may need some certain percentage availability, but if you've been at 90% uptime forever and the services have only been running for a second each, the cache is basically useless. So that's yet another really, really difficult hurdle to get to. And then finally, there's everything. So that's where storage, basically everything except Mesos is running on Mesos. And as Ben discussed, they're working on storage primitives, and that's basically what we're working towards there. So today, Twitter is basically right on the cusp of sensitive services. And this has actually been the guiding feature for a lot of the SLA work that I mentioned earlier, so that we can actually prove to things like cache users that we will keep your application up, not in a percentage, but also in a temporal way, so that your caches are warm and you can actually serve things reliably. And so while trying to put together some numbers, I noticed that we have kind of an interesting exponential relationship between different sort of aspects of the system. Our team supports, I would say, 10 to the 2 users, and these are kind of vague metrics. We have about 10 to the 3 jobs, 10 to the 4th machines, and 10 to the 5th tasks. And some of those are high on that magnitude, some of those are low. And then below that, we have 10 to the 1 Aurora developers. And that's sort of a rounded thing. And I'm wondering if anybody can guess what's 10 to the 0. Well, that's the mathematical yeah. No, it's the number of SREs. And I just want to really emphasize that. I'm so proud of this, that we have so few SREs that are supporting the platform that runs Twitter.com. And I think that's a huge testament to Aurora. I think that's a huge testament to Mesos, that we've put that much stock in this system. It's that important to our infrastructure, and we have this few people actually supporting it and maintaining it. And to be specific, we have 3. So that's it for the content of my talk. I'd encourage anybody that's interested to get involved, to check out our code, to check out our docs. The docs are rendered on GitHub in Markdown. We often hang out business hours in Pound Aurora on Freenode, and of course we have a mailing list. We're trying to do more releases. We're trying to get more committers. We'd love to graduate, so we'd love anybody that's interested to get involved. And I'll take questions now. Yeah, so the question was, this gentleman evaluated Aurora a while back and noticed it was really coupled to Thermos. Some background there, Thermos is our executor. It's basically a way that we define sort of complex workflows. It's really powerful, but also sort of cumbersome if you really just want to do simple things or custom things. So I want to clarify one thing, that while Aurora out of the box definitely forces you to use Thermos, the coupling is actually very, very, well, basically not there. As far as the scheduler is concerned, there is no such thing as Thermos. And this is just a case of basically Twitter employees working for Twitter. We really do need to do more of the open source specific stuff. And I think supporting a generic executor, supporting the command executor would be pretty trivial, but it does require some code changes, and basically some minor ones. There are some issues with that. Like I mentioned, the GCA executor, you really have to be a part of the Thermos ecosystem to make that work. So you do give up a little bit if you don't use Thermos. But, and specifically with regards to Docker, you mentioned you want to integrate there. I know there's at least 2 different use cases of using Docker with Aurora, and I think one of them we're going to hear a little bit about today. Sure, the question is if I can give some more detail about how we do preemption and how we enforce quotas. So basically, quota enforcement happens at the edges of the system. When somebody tries to schedule a job, we basically look at the things that they've asked to run that are production, and basically the slack that they have in their quota. So it's sort of a one-time thing to get into the system. We do a quota check. And basically, once you're there, you're kind of in the walled garden. So we don't enforce quota anymore at that point, but we do then use that production bit. So you're only charged quota when production is set to true. And then basically at that point, when you're in that scheduling loop, if we fail to find any resources available to schedule your task, we then look at all of the non-production things, and those are all considered candidates. And we'll basically pick one semi-arbitrarily to actually kill and make space for your task. And if you're familiar with Mesos, this is actually sort of a problem. And Aurora has sort of a history of being kind of a singleton framework, and this is a case of that where preemption is actually really, really hard to do effectively and reliably in Mesos. And there's some accommodations we've had to make. A number of people have bumped into issues with Aurora holding onto resources and basically starving other frameworks. And this is because we really need that to be responsive and schedule those production tasks, and furthermore not start unnecessarily preempting tasks. And then the other big issue with preemption is when we do preempt and clear out that resource, if there are other frameworks, there's no guarantee that we can actually get that offer back. Somebody else might get it before us. So I think long term there are some issues that need to be ironed out, but that's kind of the fundamentals, the mechanics of how the preemption works today. So the question is, what do we do once we've actually killed the task? We basically earmark that slave ID. So we have a volatile store that says if another offer comes for this task ID or for this slave ID, it's reserved. So that's how we pick up that same offer when it comes back around.